Spectroscopy is the study of how light interacts with solutions and objects so you can see different colors. The solutions here are all copper sulfate, but by varying different properties, they all look different. This is because light is interacting with these solutions in a different way, causing them to appear different. Light that interacts with a sample is measured using a spectrophotometer. It's this instrument that gives a certain amount of light that passes through the solution, and the amount that gets through is measured on the other side. The solution itself is placed in a special test tube called a cuvette. This is then placed in the spectrophotometer, and the resulting percent transmittance, or the amount of light that passes through to the other side, is measured. By looking at what affects the different levels of transmission, you can get a good sense of what the different properties are for that specific compound.
Light interacts with everything from different solid objects to chemical solutions. And it's this interaction of light with different chemicals that is the study of spectroscopy. Spectroscopy is when light interacts directly with chemicals, either in chemical solutions or objects. Light itself typically is white light, so light coming from the sun. And this consists of all different wavelengths. And in spectroscopy, typically a single wavelength or a single energy of light is selected, and it's seen how the chemical will interact with that particular type of energy light source. So light in spectroscopy and in spectrophotometers refers to or looks at light that's transmitted and light that's absorbed. Transmitted light is just kind of like it sounds. There's a light source and the chemical solution. The light passes through the solution, and some of it, not all of it, is transmitted through to the other side. The reverse of that is the light that is absorbed by the solution. The light energy comes in, it's blocked by the solution, absorbed by those chemicals, and then that increases the energy of those chemicals and can cause various different things. Either change in energy levels of the electrons, it can change how fast or how often chemical bonds vibrate between atoms, or even just how the molecule itself rotates around in the solution. And how the light interacts with the chemical will depend on what wavelength and what energy of light that's being used. Absorbance and transmittance are not linearly related. While transmittance is the amount of light that passes through to the other side, absorbance is the amount of light that's blocked. It's not a direct linear relationship. They are logarithmically related to each other. So as the transmittance decreases and the absorbance increases, it's increasing by a greater amount at this low percent transmittance. And they're related through this equation. You can easily convert between one and the other using this equation here, where absorbance is equal to 2 minus the log of the percent transmission. And this percent transmission is the whole number. So if the percent transmittance was 60%, the absorbance would be 2 minus the log of 60. You don't have to convert it to a decimal. It's easier to measure the percent transmittance because usually a detector in an instrument is detecting how much light is coming in, and that is linearly related, and then it can be converted through the log to absorbance. So logarithms are used in a number of different spots in chemistry. You won't use them a lot in this course, but there are a few places where they come up. One is in spectroscopy, converting absorbance between absorbance and concentration. But the other thing, or the other place that you'll see these is when you're looking at acids and bases, where the pH scale is a log scale of concentration of acid. So looking at the log scale, you have -4, -3, 2, 1, 0, 1, 2, 3, 4, 5. This is how it matches up with a linear scale. You're looking at how many digits are there in the final number. In the case of 0, it's 1. And in the case of a log of 1, that's 10, then 100, 1,000, and so on. So when we're looking at spectroscopy and how things relate, how light interacts with different chemicals, we'll look at the absorbance. How much light did the chemical block and absorb into itself and increase its energy by that amount? There are 3 primary things that will affect the absorbance of a solution. First off is the concentration. You can see this in things like soft drinks or beverages, where if you have it in a very high concentrated form, it's very, very dark. But if you add a bunch of water to it, the concentration has gone down and now it appears a lighter color. It will absorb less. Similar is the path length. If you have a solution in a large, wide container, looking through the side, it will look very dark. But if you pour that same exact solution into a small test tube, you can look right through it and it will appear lighter. It will absorb less. The reason for both of these is that in either case, the light trying to get through from one side of the container with the solution to the other will need to pass through more molecules, either in the form of a higher concentration of molecules in the same distance, or it has a greater distance to travel, thereby increasing the chance that it's going to hit one of these molecules. The last thing that will affect the absorbance is the molar absorptivity constant. And this is just a constant that's related to different chemicals. Each chemical will have its own pattern of how it absorbs light and how it interacts with light. And that changes also with the type of light. So an individual chemical will have a different molar absorptivity constant at every single wavelength of light. And these patterns are very unique for different chemicals and are used a lot in identifying which chemicals you have based on the patterns of absorbance. The 3 properties that affect absorbance can easily be seen. Concentration and absorbance are directly related. As concentration increases, so does the absorbance. The solution on the left is highly concentrated, while the solution on the right has a concentration of 0. Absorbance and path length
is also directly related. These two solutions are the same concentration and appear the same shade of blue, the same intensity. However, when looking at a different angle, the solution on the right appears much more deeply colored as the absorbance has increased due to the molar absorptivity constant also changes the absorbance. While at the same concentration, the reaction with aqueous ammonia solution creates a much more vivid and dark color, making sure the absorbance has increased. While these two solutions are the same concentration and the same path length, the absorbance is different based on the difference in chemicals.
As it was seen, both the molar absorptivity constants, that's the wavelength or just the chemical itself, the path length, and the concentration will change the absorbance of a solution or how dark it seems. The relationship between these three is called Beer's law, where all of them are linearly related to the absorbance. If the path length doubles, the absorbance will also double. If the concentration gets cut in half, the absorbance would also get cut in half. They're linearly related to each other. However, this is only through up to an absorbance of 1. Remember, absorbance and transmittance are linearly related. That means that after an absorbance of 1, it starts to taper off in a unique way, in a logarithmic way, and is no longer linear. So when you're looking through and using and relating absorbance and concentration, you need to make sure that any absorbance value is below a value of 1. So there are two different types of absorbance graphs that are used in spectroscopy. And one of the big ones for identifying things is the absorbance spectrum. And this is a graph of absorbance versus the wavelength of light used. Everything else in this case is being held the same. So it's at a constant concentration, a constant path length, and a constant chemical. The only thing that's changing is the type of light, the energy of light that it's interacting with. And when you plot this, each chemical has its own unique pattern, and it's used many times to identify qualitatively what chemicals are present, what types of chemicals are present, and depending on the energy of light, it can also see what types of chemical bonds are present as well. It's used very extensively, not only in biochemical assays to find different proteins, but also in organic chemistry to identify different types of bonds and different chemical groupings on a larger molecule as a whole. Typically, the wavelength that has the highest absorbance reading, that the maximum wavelength, is used to prepare calibration graphs, because at this wavelength, a small change in concentration will give a larger change in the overall absorbance. This is the full range that it can do. So it's more easily seen and detected in the next graph. The other thing for the next graph, preparing calibration graphs, is used with dilutions. So based on this image, you can see a low concentration is very light, a high concentration is very dark. So we're looking at how the light interacts. It is interacting more with this concentrated sample and less with the lower concentration sample. When you're looking at dilutions, especially in chemistry, you're using the molarity calculation. Molarity is moles over liter. And when you do a dilution, you're starting out with a high concentration, you're taking some volume of this high concentration and adding more water to it or adding more solvent to it to dilute that amount. The total number of moles did not change, just the volume. But because the volume changed, the concentration will also change because that same number of moles are now spread out over a larger volume. In a typical sample of dilution would be something like this, where there's a 30 milliliter sample of a 0.500 molar solution of copper sulfate, and that's mixed with 50 milliliters of water. So what is the final molarity? So first you have a concentration of 0.5 molar, and you have 30 milliliters of it. Afterwards, at the very end, you have a total volume of that 30 milliliters plus the 50 milliliters of water for a final total volume of 80 milliliters. Moles in both cases are constant, and you're trying to solve for what is the final concentration. So you can use the molarity equation twice to go through and see exactly what is happening. You have and to start with, you have a concentration and a volume, so you can determine how many moles this is. When you have that number of moles, you can spread it across the new volume of 80 milliliters, and you end up with a final concentration, a final molarity in this case, of 0.1875 molar. So in this case, you're looking at this dilution, and you're using two molarity calculations where moles are equal to each other. This is where M1 V1 equals M2 V2 comes from. This simplified equation is used only in dilutions. It has no other use anywhere else, just when you're diluting something, because in this case, the moles are constant, and therefore the ratio between moles and liters varies and affects the concentration in an inverse way. So in something like preparing a calibration curve, many times in chemistry or in a lab, you're preparing a calibration curve using concentration. You have a higher concentration to start with, and you are making various dilutions to that concentration. And then when you have that series, so in this case, there's a whole series of different solutions at different concentrations, you can then measure a property based on the concentration. In this case, in a lab like this, it's measuring the absorbance based on the concentration. And calibration curves are linearly related. Beer's law has a linear relationship between absorbance and concentration, so long as the absorbance is below 1, and this can be seen. When plotting the absorbance versus the concentration, you can see a straight line, and this is how you can relate these two properties, concentration and absorbance. Now you can do this and determine a slope, and from the equation of that line, the equation of this line, you can relate the two properties. Given an absorbance, you could figure out what would the concentration be. If you're given a concentration, you can calculate what the overall absorbance would be. Now, these lines aren't going to be exactly exact with every single data point. These are the lines of best fit. And you're going through and preparing calibration graphs using the trend line. Now, in this example, I plotted a line where the equation is y equals 0.005x. This was just the calculated equation from Excel. Notice also that there is no other term. This is a y equals mx plus 0. There is no b term. The y-intercept is 0. At a concentration of 0, anything, it should read an absorbance of 0. There are no molecules there to absorb any of the light. So when you're using, if you were to graph by hand, you can determine the slope of a line based on rise over run. You can easily force a line to go through 0. In Excel or other graphing programs, there are different functions that can give you these values. The one that came up just through the graph only had one significant figure. And if I go through and actually use the different functions in Excel, you can get a more accurate value for this. You can use the slope function, select all of the y values, comma, then all of the x values, and that will give you a slope. And you can use the intercept function, selecting again all the known y values, comma, all the known x values. In calibration graphs, or particularly these ones in spectroscopy, it is good to force the line to go through 0. Because again, at a concentration of 0, there is 0 absorbance. And these two functions, just slope and intercept, don't take that into account. So this function right here will give, will force the line to go through 0 and then give you that slope value. And to use this as the linist function, known y values, comma, known x values, comma, type in the word false, all in parentheses. And then that would give you the y equals mx function. Looking at this, you have y, which is your absorbance, x is the concentration, b is 0, m is the slope, which is constant. And in these types of measurements, you're holding the path length constant and the wavelength constant, the molar absorptivity. So the slope of that line on your calibration graph is the molar absorptivity constant times the path length. And if you know one, then you can calculate the other. So for example, if you have a calibration graph, you have the equation for that line. If you're given a concentration, you can solve for an absorbance. You can plug in the concentration value. I'm sorry, if you're given an absorbance, you can plug in the absorbance value, solve for the concentration. But you can also determine what the absorbance or transmittance is from a concentration value. That can be plugged in directly, and you can solve for absorbance. And then the absorbance itself can be converted into percent transmittance. In today's experiment, what you'll be doing is obtaining both an absorbance spectrum and a calibration graph of a dye solution. So in the experiment, you're starting with a dye stock solution, and you're going to be preparing a number of different dilutions of this solution using a burette and volumetric flask. So a volumetric flask is used to prepare solutions because it contains a very precise final volume. In this case, in the lab, you're using a 100 milliliter volumetric flask. And there's a line on the neck of the volumetric flask, which indicates that for that particular piece of glassware, that is the mark where it is exactly 100.00 milliliters contained within that flask. So you're going to be preparing a number of different solutions and preparing them in a volumetric flask. To prepare the initial solutions, you're going to be using a burette, and you're going to fill the burette up, and then you're dispensing an amount of stock solution into the volumetric flask. From there, you'll be able to determine the final concentration. You have the initial concentration of the solution on the stock solution bottle itself. You can see what the concentration is. And initially, if you have, let's say for the first example, you have 2 milliliters of that, and of that high concentration, and then you have 100 milliliters total volume at the end, you can use the M1V1 equals M2V2 calculation to determine what is that final volume. In the experiment or in lab, you're going to be preparing 5 different solutions using 2, 4, 6, 8, and 10 milliliters of the stock solution. So you're going to be using a total of 30 milliliters of stock solution to prepare these 5 different lower concentration solutions. In the experiment, you're going to be using a burette to measure the exact amount of volume that you actually dispense. And you're making sure to read the burette out to 2 decimal places for the correct precision. When preparing the solutions, you don't have to make it exactly 2.00 milliliters, but you do need to record what is the total volume of stock solution that you add into that volumetric flask, where the final volume is then 100 milliliters.
To prepare your solutions using a burette, the burette first must be filled. You can do this using a funnel. By pouring the solution into the burette, making sure that the bottom is closed, you should fill the burette to above the 0 mark. By filling the burette above the 0 mark, you can then open the valve at the bottom and drain the burette until the solution inside is exactly at the 0.0 milliliter mark. This beginning initial volume does not have to be exactly 0, but it does make the calculations a little bit easier. You just need to make sure what is the starting initial volume of the burette. You can see that by draining a little bit from the burette first to make it read 0, the tip of the burette is now also filled with liquid. The burette is calibrated to deliver a precise amount of volume, assuming the tip of the burette is already full. By doing so, now you're ready to use the burette to distribute your solution. The different solutions are prepared by dispensing the stock solution from the burette into a volumetric flask. The solution can be dispensed directly into the volumetric flask. By opening the valve at the bottom, you can drain the solution until the volume reading of the burette is the appropriate amount. Initially, for the first solution, you are dispensing exactly 2 milliliters of the stock solution into a volumetric flask. If you dispense slightly more or slightly less than 2 milliliters, this is also correct. You just need to make sure what is the actual volume that was dispensed into the volumetric flask. When preparing your solutions, the solvent used is water. Initially, you can pour a large amount of water into the volumetric flask. However, as the volume in the flask increases and gets closer to the mark on the volumetric flask, you will need to dispense the water slower. As you get close to the mark on the flask, you should dispense water using your dropper bottle or through a dropper pipette. Once the water is exactly at the mark on the volumetric flask, it contains a total volume of 100.00 milliliters. You can then stopper the flask and invert it to make sure that the solution is thoroughly mixed. At which point you can save some of your solution and then make other solutions using more of the stock solution. In total, you will be making 5 different solutions in volumetric flasks at varying concentrations of the stock solution.
Once you have the solutions prepared, you're going to be measuring the absorbance and transmittance of them using a spectronic 20. And this is the instrument that would be in the lab room. So you can see here the different parts of the spectronic 20, the different readouts of both the wavelength, percent transmittance, the sample holder where you will place the different samples, the adjustment for wavelength, and then the on-off switch, which is the left-hand knob, and the left and right front knobs are also used for the calibration procedure. To calibrate a spectronic 20, this needs to be done each time you turn it on, as well as every time you change the wavelength of light that's being used. So you'd first turn on the instrument using the left knob and adjust it to the appropriate wavelength that you're going to be using. Make sure there is nothing in the sample holder and that the sample holder is closed. You can then use the left-hand knob to dial to a percent transmittance of 0, and then place in your solvent. Typically, this is water, but in other situations, it could be whichever type of solvent you're using to dissolve or dilute your particular sample. In this experiment, you're using water. So water, tap water, is going to be your solvent. That would be the cuvette containing that sample would be placed inside the sample holder, making sure that it's lined up correctly. And then the right-hand knob is dialed to 100%, indicating that the solvent itself it's telling the instrument that the solvent, all light is able to pass through that. And that gives you a 2-point calibration. You can then take your solvent out, place your sample inside the cuvette holder, and record the percent transmittance.
Operating and calibrating the Spectronic 20 is done with the 3 control knobs on the instrument. The left-hand knob is used to turn the power on to the instrument itself. The top control knob changes the wavelength of light being used to measure the absorbance and transmittance. At this point, I can adjust the wavelength to 480 nanometers. To begin the calibration process, which is done at each wavelength, you can first use the left control knob to adjust the reading to 0% transmittance. This is done while the chamber is completely empty. When the instrument is adjusted to a 0% transmittance, you can then take a cuvette containing your solvent, typically water, and place it in the holder. You'll notice that these cuvettes all have a line on the cuvette itself. This is to make sure that you always place the cuvette in the same direction and orientation each time you place it in the spectrophotometer. The spectrophotometer itself also has a little mark, which you can line up with the cuvette. With the cuvette containing your solvent inside the spectrophotometer, you can now use the right control knob and adjust this to 100% transmittance. This is a 2-point calibration where it tells the instrument when the light is off and there is no sample, there should be 0% of the light getting through to the other side. Likewise, when you put in your solvent, you want it to read 100% because at this point, you're only interested in the absorbance of your sample, not the solvent. So any absorbance that's coming from water itself can be corrected for. There's usually a small amount of drift associated with the actual value, so plus or minus 0.2 for the calibration and measurements is acceptable. You can then remove your solvent cuvette and place your sample cuvette inside. Again, making sure that the markings are lined up on the spectrophotometer. When this is done, you can then record the percent transmittance of this particular sample. The percent transmittance can then be converted into an absorbance for you to either determine concentration or molar absorptivity.
So you've prepared the 5 different dilutions of that initial stock solution. And what you're going to be doing first is obtaining an absorbance spectrum. And an absorbance spectrum, as I said, is a graph of absorbance on the y-axis versus wavelength on the x-axis. So you're going to choose either your solution number 1, 2, or 3 and calibrate the instrument at 400 nanometers and then measure the percent transmittance of your sample that you choose. You're then going to be increasing the wavelength by 25 nanometers to 420 nanometers, recalibrating the instrument and obtaining the percent transmittance of your sample again. You're going to do this over the full range of the visible region of light. You'll go from 400 nanometers all the way up to 700 nanometers and record the percent transmittance of each one of those increments of 25 and convert that to an absorbance. Then you'll be able to plot all of those points on a graph to obtain an absorbance spectrum that is unique for that particular sample. As with any graphs, they should be properly labeled, and make sure to include the name of your sample as well as what concentration you're using to obtain this absorbance spectrum. The next graph that you're going to be obtaining is the calibration graph. When you prepared your solutions, you made 5 different concentrations. And now you're going to obtain the percent transmittance at a single constant wavelength for these different samples. While in an absorbance spectrum, the concentration remains the same and the wavelength is being changed. In a calibration graph, the wavelength remains the same and the concentration is changing. And you can see that the shape of the graph is very different between the two. So in lab, you're going to be dialing the wavelength to 480 nanometers. And again, making sure that it's calibrated at 480 nanometers. And then one by one measuring the percent transmittance of each of your 5 prepared solutions. You can then plot absorbance versus concentration of your sample to obtain this calibration plot. And it should be a straight line. The line itself should go through 0 because at a concentration of 0, there would be no light that is blocked in the spectrophotometer, so the absorbance reading would also be 0. And again, as with other graphs, you should make sure that everything is properly labeled, including the sample name and what's being held constant in a calibration graph, which is the wavelength. The last part of the experiment itself is looking at an unknown sample. So everything you're working with is the same compound, but they're all at different concentrations. And what you're going to be doing is taking choosing an unknown sample. It's all of the same dye, but at an unknown concentration. And you're going to determine what is that concentration based on your calibration graph. You'll obtain a sample and measure the percent transmittance at 480 nanometers. You'll measure that 3 times. And that way you can obtain from those 3 measurements using the equation of your line that relates absorbance and concentration. You can determine what is the concentration of those 3 trials based on its absorbance. And then you can obtain an average for the 3 different trials. So that's really what you're going to be doing in lab. You're going to be preparing these solutions, measuring the percent transmittance at varying wavelengths, converting that to an absorbance to obtain an absorbance spectrum, and then measuring percent transmittance, converting to absorbance at a single wavelength, but varying the concentration to obtain a calibration curve, and using that calibration curve to determine the concentration of an unknown sample.
As you work through the experiment, you're looking at how light interacts with these solutions and how it affects what you actually see, from different path lengths and different concentrations to different environments that the solution or compound happens to be in. All of these affect how light interacts and the color that you see.